Welcome. This is lecture 55. So in the next this lecture and the next 5, we will look at syzygies, called free resolutions, and what information can be gleaned out of computing free resolutions. Okay. Some information that can be gleaned out of. There are many other things that can be obtained by looking at a free resolution. We will see an introduction to that. So we are going to start free resolutions. So we will not be able to prove many things properly because to discuss these things, one needs to spend some time developing basic notions about complexes and homological algebra, which we have not done, and we do not have the time now to do this. So there will be a few results that we will assume, and then we'll see how to use them or okay, so recall, so I have not yet defined this, but let's so recall that, okay, so if you have an ideal I inside a polynomial ring, K adjoint some n variables, okay, then we only looked at this case, but this is true more generally. Then the relations among the R linear relations among a generating set let's say F1 through Fm. Okay, so this is called syzygy of this is what we looked at in the last lecture, syzygy of F1 through Fm, okay, can be obtained by looking at the kernel of the map, can be determined by looking at surjective, looking at the kernel, looking at the kernel of surjective map, R linear map, free module on rank M to I. Okay, a basis element here goes to Fi. Okay, so this is E1 through EM is a basis. Okay, so this is a basis for this module, and if we map EI to Fi, then the syzygies of Fi are precisely the elements of this kernel. Okay, or are. Okay. So this is what we saw in the last lecture. But notice that this is the same for modules also, because all that we are using here is an R linear map from a free module to I. We are not using the fact that this is an ideal. All that we are using is that it is an R module. Okay. Okay. So same argument works for modules also. Again, we will only be concerned about finitely generated modules. That's much better theorems in that context than otherwise. Okay. So how would we, and why do we have to do this for modules also? Okay. So one of the things that we would want to do is, so given, even if you're given an ideal, let's say generated by m elements. Okay. We can get a free module of rank m to surject onto this. This would give the kernel of this map. So let's call this map epsilon. Okay. Kernel of epsilon is actually gives the syzygies of I, of really the generating set. Okay. But we'll see that it is actually I. Okay. Now, so let's write that thing here. I'll write it slightly below here for a purpose. Okay. Okay. So now this is also finitely generated, but it's no more an ideal. Okay. So kernel of epsilon is finitely generated. Submodule of Rm. Okay. And typically m has to be greater than 1. So this is not an ideal at all. Okay. But we can repeat the same procedure. That is, say kernel of epsilon needs m1 generators. Okay. So then we take a free module of rank m1, map it surjectively onto kernel of epsilon, and kernel of epsilon of course sits inside here injectively, and the composite map we call it, let's call it partial 1. Okay. So what have we done? We have constructed a presentation of I. This we have done earlier. Okay. So we have constructed a presentation of I. Okay. We talked about finitely presented and all those things. So this we have seen this earlier. Now we can repeat this. This is a surjective map, its image here, and delta is a composite. So the kernel of the surjection from Rm1 to kernel of epsilon is same as the kernel of delta 1. Okay, so kernel partial 1 is kernel of the map from Rm1 to kernel of epsilon. That's the way delta was defined. Okay, so therefore we can now consider here kernel of partial 1, okay, and then some Rm2 surjecting onto this, and this is anyway. So what we're doing is we are getting a presentation matrix for kernel of epsilon using this map, okay, not just some, okay, because we are using this map in constructing this. We are looking at the kernel of either of these maps, partial 1 or the surjective map onto kernel of epsilon. Okay. That we are using to get a presentation matrix here, and so then let's call this thing partial 2. Okay. And this we can repeat. Okay. So then take Rm2 surjecting onto kernel of partial 1. Okay. This gives Rm2 to Rm1, okay, which we called partial 2 there. Sorry, Rm2 to partial 1. Okay. And then this is to Rm to I to 0. Okay. So note that this is an exact sequence. This is an exact sequence. Okay. Sorry, this is partial 2. Okay. This is epsilon. Sorry, the map from Rm to I is epsilon, Rm1 to Rm is partial 1, and Rm2 to Rm1 is partial 2. So what do we have? We have epsilon is surjective. Okay. Kernel epsilon is image of partial 1, and kernel of partial 1 is image of partial 2. And in fact, we can continue this. Okay. So we can continue this to get what is called a free resolution of I. Okay, and we could have done this for it. And notice that in this process we had to learn to present not just ideals but also modules. Okay, so we may start with an ideal, but immediately after that we have to start worrying about modules. So we may as well learn about modules. And as we mentioned earlier, nothing that this is an ideal is used. All that we have used is that this is in our module. Okay. Okay, so let's make a definition. So before we define, we need to, not for the purpose of this course, but in general, when we want to do this, we need to discuss something more general than exact sequences. So definition. This is only, for us, this is just a language, that's all. We're not going to study this or worry about these issues in this course. So, but let's better we understand what this means. The words mean. Okay, complex. I mean, technically a chain complex, but we'll just always refer to as complex, or more precisely, chain complex. Okay, of R modules. Okay, is a sequence of R modules and R linear maps. Okay. So again, we will only consider special cases. So we will assume that the complex ends somewhere. On the right, okay, of this kind. So these are R linear maps and such that. Okay, so let's call these maps, let's say mu2 going from M2 to M1, mu1 going from M1 to M0, and so on. Okay, so mu3 here, such that mu I plus 1 is 0. Okay, so that is kernel of mu I contains the image of mu I plus 1. Notice this is how the composition will work. Okay, we apply mu I plus 1 first and then mu I. Okay, this is a composite map from mi plus 1 to mi minus 1. Okay, so this is what is called a complex. So, and we say that a complex is exact if so we'll denote this by, M with a bullet, a thickened dot at the bottom. Okay, and if we need to specify the map, sometimes we would not need, we will also just by this if we need, otherwise we'll just say M. Okay, and remember that our convention is that mu I is the map from mi to mi minus 1. Okay, and these are our linear maps. Okay. So then the homology of M, again it depends on the maps, not just the modules. Okay, is hi, and this is for all I. I is kernel of mu I modulo image of mu I plus 1. Okay. But kernel of mu I contains the image of I plus 1. So the quotient is what we are interested in, and this is for I in Z. But often the modules that the complexes that we are concerned will be 0 after a while. It may not be 0 at M0 itself. Okay, it could be like some M minus 500, but it would still be 0 after a while. And so this is, okay, but nonetheless we can still define it for all Z. Okay, so then say that a complex M dot is exact if all the homologies are 0. Okay. So for example, okay, so then we can make the definition of a free resolution. Okay, so definition. We can make a proper definition of free resolution. Okay. Free resolution of an R module M is a complex. Okay. So this will end at some F0, F1, F2, and it may go infinitely infinite to this side, but we usually put this thing here. Okay, such that okay, hi of f is 0 for all I different from 0, and h0 of f is isomorphic to m. Sorry, that's not enough. That doesn't make it a free resolution. Such that sorry, let's put 1, 2, and this should have been 0. Fi is a free R module for all I. Okay, so that should have been, I should have stated that first. Fi is a free R module for all I. That's why it's called a free resolution. And in this complex, at these places there is no homology. There is a homology here, which is isomorphic to M. So just a note. Okay, so some books might, not might, some books refer to the, so this F as we defined is not exact. It has exactly one, it is not exact. It has one non-zero homology, and that is isomorphic to M, and it is at the rightmost end. Okay, so this is how our convention is. This is what we will say. Some books refer to the exact sequence. So we put everything as above, F3 to F2 to F1 to F0. Now, what does it mean to say that the 0th homology is M? What does it mean to say 0th homology is M? Okay, so it means that is isomorphic to M. It means that the 0th homology here is everything goes to 0 here. This is the 0 map. Okay, and the image of this map is the image of this. So H0 is the co-kernel of this last map, F1 to F0. Okay, so then if you write M here, so exact to M to 0, it becomes exact as a free resolution of M. Okay, so we will, of course, we will refer to this condition as free resolution. Some books, if you read, it might actually write this as a free resolution. But it will be clear from the context whether the book is using this convention or the other convention. Okay. So this is just a. Okay. So now we want to define what is called a minimal free resolution. mean, so far, whatever I have said just works for any Noetherian ring and finitely generated module. In fact, we have even used finitely generated anyway. So this is some very general, in some large generality. But now we so graded. So two things that we want to emphasize: minimal graded free resolution. Okay, so now we will restrict ourselves to a graded ring. I mean, we will restrict ourselves to the polynomial ring, but most of it will again work over rings in which graded rings, n graded graded rings, in which the zeroth piece is a field, okay, and finitely many generators, all of which have positive degree. Okay, so it'll but we will restrict ourselves to the specific situation. Okay. So here is a lemma. Okay. So what is okay? So let f1 to f0 to m to 0 be a graded presentation of finitely generated graded R module M. So we are given a finitely generated graded R module and we take a graded presentation. So we take a homogeneous generating set for M and then we map that many generators onto M, look at the kernel, then we take homogeneous generators for the kernel and then correspondingly build F1. Okay. So these things are the free modules are graded and the maps preserve degrees. Okay. So that is all the two maps here. This is anyway 0. So okay. So this means that is FI are graded free modules and maps preserve degrees. This is what we mean by a graded presentation. Then the following are equivalent. Okay. 1. Rank, so this is a free module, F0 and F1 are free module. Rank of this is equal to the minimum number of generators for M, the size of a minimal generating set of M. It is finite. Okay, so this is the definition. Okay, so mu of M. So this is the first hypothesis. Rank of F0 is mu of M. 2. Let's call this map partial 1, the presentation map. Okay, image of partial 1 is inside M F0, and 3, if we write partial 1 as a matrix, then its entries are homogeneous elements of the maximal ideal. In other words, it does not contain any units. Okay. So 2 if and only if 3 I leave as an exercise. It is just rewriting what means to say that it just trying to understand what it means to say a map lands inside M times F0. Okay. So this 2 if and only if 3 so proof 2 if and only if 3 exercise, okay, and so 1 if and only if 2. Okay. So let K be the let's label this map also. So let's just rewrite the map. So the map is F2 to F1 is partial 1, and this map let's call epsilon. Okay. So let K be the kernel of epsilon. Okay. So then let K be the kernel of epsilon. So then we have a map, an exact sequence, K to F0 to M to 0. This is the map epsilon. This gives M mod MM. This was, we have seen this earlier, F0 mod MF0, and then K mod MK. This need not be injective, but we get such a map. Okay, so we cannot fill this back inside here, but so much of this is exact. Okay, but the hypothesis is that, so now what is the hypothesis? Rank, before we get into the hypothesis, rank over K of F0 mod MF0 is rank over R of F0. If it's a free module, then just use the same basis, you will get the quotient module. Okay, and mu m by Nakayama's lemma is equal to rank of over K of M mod mm. So the hypothesis is that these two numbers are the same. In other words, we are saying that this map is, this is an R linear map, it is also R mod M linear map. So what we are saying is, so let's call these things, let's just call that map epsilon bar. So then what we are saying is that 1 if and only if, so one says these two numbers are the same, so 1 if and only if epsilon bar is an isomorphism. Okay, so that's one place. We have already used, for this statement, we have already used Nakayama's lemma, so M is finitely generated. So we've already used it, but here is another place where it's used, that these are finite dimensional vector space. So if there is a surjective map, then it must also be injective. Finite dimensional vector space of the same rank, so a surjective map must also be injective. Okay, so therefore, this is an isomorphism. So in other words, the image of this map, so let's call this thing delta 1 bar. Okay, image of delta 1 bar is 0. So this is an isomorphism, okay, if and only if okay, image of delta 1 bar is 0. But what does that mean? Image of delta 1 bar is, well, it is just image of K inside the quotient. So it is just K plus MF0 mod MF0. So this is true if and only if K plus MF0 mod MF0 equals 0. Okay, but that is the same as K is inside MF0. Okay, but which is what we wanted to prove. So this is, but remember delta 1 is a surjective map onto K, so this means that image of delta 1 is inside MF0. Okay, image of delta 1 is K. Okay, so this is the proof. Therefore, if you construct a free resolution picking minimal number of generators at every stage, we would get a minimal free resolution. Okay, so then let's summarize these things in a proposition. Let M be a finitely generated graded R module. Okay, then M has a minimal graded free resolution. Okay, and what does that mean? It means F0, F1, F2, and so on. That is, so what is that is a complex. Okay, this such that a complex of finitely generated graded free modules Fi and degree preserving maps such that, okay, so we also need to label the maps partial 1, partial 2 and so on, such that for all I greater than or equal to 1, image of partial I is inside MFI. Okay. So this is the minimal part, okay, and HI is 0 HI of the complex. So we defined it as a complex is 0 for all I different from 0, and H0 of M is H0 of F is isomorphic to M. So this is just saying it's a free resolution. Okay. So all the ranks of these are finite. The maps are minimal in this sense, and there is no homology all the way till here, and the homology here, there is no homology in these red parts, and the homology in the green part is M. Okay, so such a thing exists. So this is what we want, and we want to define two things. Okay, so first is a theorem. We will not prove. Okay, so now we do want R to be. And so far, this works even in the generality of n-graded rings, finitely generated algebras over a field. Okay, not necessarily polynomial rings. Graded. Okay, degree of xi equals 1. M finitely generated graded. Okay, then M has a minimal graded free resolution, of length at most n, the number of variables, I mean the rank of n, the dimension of R. Okay, so this is, and we will not. So this is called Hilbert syzygy theorem. So in the next lecture, we will go back to computational ideas behind finding resolutions, and then we will try to sketch a proof of how one could prove Hilbert syzygy theorem. Although this is typically proved using some after first course, after some understanding of homological algebra. Okay, not in a computational way. I mean, although Hilbert's original proof itself was non-homological because homological algebra was not understood at that time. Okay, so just one more definition, and then we will look at. Okay, we define the graded Betti numbers beta ij of M to be the number of copies of R minus J. This is the free module, rank 1 free module with a generator of degree J. So number of copies of in Fi. And you might wonder, there's so many choices made in the construction earlier. So why is this even well defined? A fact is that this does not, in a minimal free resolution, minimal free resolution, graded free resolution. Okay, and the fact is that this does not depend on the choice of minimal graded free resolution F. Okay, choice of F. Again, we are not in a position to prove it, but we will uses thing for now. Okay, so now let's quickly look at a Macaulay example. Okay, so here is a polynomial ring in two variables, x and y. Okay, ideal we want to take x squared and xy. So then we ask, okay, so then we ask, the command is res, which is an abbreviation for resolution. We ask for the resolution of I. Okay, so note that it produces something called chain complex. But note here that it is not a resolution of I, it is really the resolution of R mod I. So, okay, so please keep that in mind. So we call that thing F. Okay. If you want to see the maps in F, there is a command called, there is a key for a chain complex called dd. Okay. So you can ask f dot dd. There is no space, it is just f dot dd. So it will put out the maps. The first map is, so as I said, this is a resolution of R mod I and not R mod, not of I. So the map is R2 to R1, in which base generator here, the first basis element gets multiplied to x squared times the basis element here. Second one gets multiplied to xy times the basis element here. In order to make this degree preserving, if the generator here has degree 0, the generator here must have degree 2. Okay, so that's what this thing says. So in the second map, this is the map from F2 to F1. The map is this, okay, and it says that the target of the map, the basis elements have these degrees 2, 2. Okay, so this just says a basis element. A basis element here gets multiplied to minus y times the first basis element plus x times second basis element, and both basis elements have degree 2, and hence the basis element here will have degree 3. Only then you can make this this map degree preserving, and the final map is 0, and it shows these things. Okay, so don't worry about chain complex map now. Okay, so then we ask for Betty of the free resolution, so it produces this, and this is what we had discussed. Okay, so we need a brief explanation of what this means. So what is in position I? So column indices are the position in the free resolution. So think of this as being written from the right to left. The arrows are going from the right to left. Okay, so exactly how we saw it in the displays earlier. Okay, so the F0 is rank 1, F1 is rank 2, and F2 is rank 3. That's what this total row means. So the column indices are where in the free resolution we are looking at. The row indices has the following, this is how it is done. The number in column with index I and row with index j is beta I plus j. So one should keep that in mind. Okay, so here it says beta 0, 0 is 1 and beta 0 j is 0 for every non-zero j, and that is another way of saying F0 is R. Okay. Next, beta 1, 2 is 2 and beta 1j is 0 for every j different from 2, and that's just another way of saying F1 is R minus 2 with a direct sum of 2 copies of itself. Okay. So then this is what that is because I is minimally generated by 2 quadratic polynomials, we needed to choose this. Okay. There is not much choice. And beta 2, 3 is 1, and for other j, beta 2j is 0. Okay. So equivalently, F2 is R minus 3. Okay. So here is a proof which I will anyway explain, give it as an exercise. You should work this out. So if you write the basis for F1 as E1, E2, then E1 goes to x square, E2 goes to xy, then R1, R2 be a syzygy of the, be a relation among them, R1, E1. Okay. But then we apply the map partial 1 going from F1 to F2, so then we get this, okay, x1, so this is just applying the map, E1 goes to x square and E2 goes to xy, so we get this relation. Okay. We can assume that they are homogeneous, but but because of this, now this is a relation inside R, so you can divide by x. So then you get x R1 plus y R2 is 0. Okay. So from this, y R2 is divisible by x. This is a UFD, so x must divide R2 because it doesn't divide y. X is irreducible. So we can write R2 as x times s. for some s in R. Then we put that back, we will set R1 is minus y times s. This is just putting that thing back. Okay? And therefore, an element of the kernel, which was R1E1 plus R2E2, remember it's the kernel of that thing, is s times YE1 plus XE2. And that's exactly what, that's exactly what this map says. Okay? The kernel of this map is generated by minus y1 times, is generated by the image of this, and image of this is minus y1 times e1 plus x times e2. Okay? So this is the end of this lecture, and in the next lecture we will look at computing syzygies, etc. Then we will try to learn some, do some more examples.